We've looked at direct proportion and we've seen that we get a straight line going from the origin. We understand that one increases, say, by 20% and the other one is going to also increase by 20%. That's what it means to be directly proportional. We've introduced notation and then we've introduced the idea of writing y equals kx or even y equals kx squared if y and x squared are in direct proportion. Today we're going to look at something that's related and we'll see why, and it's called inverse proportion. So you might want to think, what does that mean? What does this inverse mean? But it'll make sense once we go through it. Okay, we're going to look at a scenario. So a rectangle with base 12 and height 5 has an area of 60. And this can be plotted on a graph like so. I can find my base of 12. This is 12.5. It's going to be a bit less than that. So I'm going to be drawing a line, a little cross around here. And we can say, right, I want to find all the different bases and heights that give me an area of 60. So this is what I want you to do. Pause the video, please draw a graph and see if you can get it sorted. So something that you might have done, there's different ways of doing this, is you might have drawn a table. You might not have, but you know, I did when I did it. So I've plotted some different bases. There's more that I could have done. Obviously 1 and 60 would work, but that's not going to fit on the graph. But I get all these different pairs that multiply to give 60. And if I plot those, then I get a graph that looks a bit like this. And then I've only plotted some of the points. In actuality, there's an infinite number of points. Some of the numbers will be fractions, some of them will be irrational, like the square root of 60 times the square root of 60 will give me a square with an area of 60. That'll be on there somewhere. And then we get a line that looks a bit like this. I hope you managed to do that. I know my line hasn't gone through all the points. It's meant to, it's just a bit hard on a computer to do that. And this is an example of inverse proportion. And this is why, because as I double the base, what's happening to the height? It is halving. So instead of now something doubling and the other thing doubling, we've got kind of the opposite going on, the inverse as such. As one doubles, the other halves. Now, if we just talk about this a little bit more, this graph, what we've actually plotted is the height times the base equals 60. That's the graph we've plotted. We could rearrange this to height equals 60 over the base. And that's actually the graph we've drawn. It's like a reciprocal function. We've looked at things a bit like this, and this is an example of one. So again, this is giving us a bit of an indication of what we mean by inverse proportion. So for direct proportion, we had like y equals k multiplied by x, but now we are dividing. So you can sort of see, hopefully, the link between direct proportion. We're going to do a little bit more to see the link. What I'd like you to do is pause the video, draw another graph with these axes, and actually plot 1 divided by the base against the height. So I've got some examples of bases already if you want to use them or use your own. Find 1 divided by each of these numbers, plot that along the x-axis, and then plot it against the height. Have a go now. So this you might have carried on with the table. This is what I've done here. I've got some different values. I've had to round them because some of them are recurring decimals. But then I plotted these against the height, and this is what you get. You actually get a straight line when you plot it. But of course you do, because we've actually just plotted h equals 60 times 1 over b, which is exactly the same as this thing here, but we've called this our x. So we've basically done h equals 60 times x. So we are going to get a straight line, and it is going to go for the, sort of in theory, it would go through the origin. The point is, of this graph is seeing another link with direct proportion. So what we have is that we would say that h is not directly proportional to the base, but it is directly proportional to 1 over the base. And that is what actually we mean by inverse proportions. I'm going to say that again. If h is directly proportional to 1 over the base, then h is inversely proportional to the base, and vice versa. If I tell you that h is inversely proportional to the base, then you can write this down straight away. And from that, we can write down, just in the same way that we did for direct proportion, h equals k divided by b. Not k times b this time, but k divided by b. In this case, k is 60, but this will hold in general. So we've looked at graphs. I'm just going to we're going to have a look, just tiny little note on this now. So just to summarize, inverse proportion is when as one value doubles, the other value halves, or as one value is multiplied by 10, the other one's divided by 10. They don't change at the same percentage like they do for direct proportion. There's a different kind of relationship. And then we say if y is inversely proportional to x, then y is directly proportional to 1 over x. And that gives us a means of then writing this symbol as before, and then writing y equals k over x. If we just compare it, it's a very similar thing going on to direct proportion. Basically, we need to know this statement here, but hoping you understand where it's come from, and now we can solve questions in a similar way to like we did for direct proportion. Now we're going to talk through 4 examples of applying inverse proportion to mathematical situations. So we need to be able to, basically, you need to know this stuff here, that if I say something's inversely proportional, then you can write this down, and then you can write down that y equals, sorry, I don't know if you can see this, so you need to write this down, and then that y equals k over x. You also need to have an understanding of this kind of shape. When two things are inversely proportional, this is sort of graph. Just to say, of course, I didn't say this already, that y can be inversely proportional to x squared, and then all I would do is, instead of having x, I would have a squared there, and things will work in the same kind of way. If I was to plot y against x squared, I would then get this kind of graph like I'm showing here. So just be aware that it's not just, you know, one quantity against another. It might be the quantity squared or cubed or square rooted. Right, let's do some examples. So a is inversely proportional to b. We can immediately write that a is directly proportional to 1 over b. It's the same thing, and a equals k over b. A and b can change, but k is this fixed constant. I don't need to say that, but it is. I don't need to write it when I'm answering a question, but it is always the case. Now find a formula for a in terms of b. Well, we've got a formula, we just don't know what k is, and that's where we need to use this condition, just like we did before. So I can substitute this in. I get 12 equals k divided by 4, and then I'm going to rearrange to get k. It's going to be 4 times 12, which is 48, and that's going to give you my answer. A is equal to 48 divided by b. Okay, this is the key equation that I've shown that the subsequent questions are going to then use. So find the value of a when b is equal to 8. I'm going to now keep the same k. That's absolutely important, but a and b could be different things. So a is now going to equal 48 divided by 8. B is equal to 8, and that is equal to 6. So I can use my inverse proportion knowledge and find the value of b when a is equal to 4. Again, I'm going to revert to this formula. 4 equals 48 divided by b. Bit more to solve this equation, so you could try and figure out, like, what do I divide 48 by to give 4, and figure out from there. But you know, if it was a horrible number, like if I had 7.5 here, then you'd need to be able to rearrange. And so we can rearrange by multiplying by b. 4b equals 48, and then you can divide through by 4, which gives b equals 12, which you could have spotted in this case, but make sure you can rearrange. And that's the answer to this question. We've used this, like, this is the key bit, and this is what you may well forget, okay? But absolutely essential, because if you can't do this bit, you can't do it, you'll get all A, B, and C wrong. So very typical sort of question. Make sure that you understand what's going on. I've talked quite a bit about the graph and why this is the case. Okay, second example. R is inversely proportional to the square of C. So that means we can write down R is proportional to 1 over C squared. Always recommend you start with this little proportional symbol. Okay, this time I've got a squared there, so R is going to equal K divided by C squared. I've even jumped into doing the question before it's asked me to. So I've got a formula, I just don't have the value of K, so I need to find it. So I can substitute in 30 equals K divided by 4 squared. That means K is going to be 30 multiplied by 16, and that gives me 480. And so my answer for part A is R equals 480 divided by C squared. Sorry, some pen strokes didn't come out. Okay, absolutely crucial formula which we're then going to use for part B. To calculate the positive value of C when R is 1920, I substitute in to this formula that I've just got. Okay, the next step, I'm just going to move some of my working up to create a bit more space. Next step is to get what C squared is, so I can multiply through by C squared. And then I can divide by 1920. And this gives me a quarter. So I can finally work out C by square rooting a quarter. Technically, it would be plus and minus the square root, but it said here, calculate the positive value of C. So I only need to worry about the positive value, the positive square root, and that is going to give me a half or 0.5. So yeah, this formula that we got here, absolutely crucial for allowing me to solve part B. Okay, one more type of question to look at. This time, we don't have some nice conditions to try and find the formula. We have to sort of use our knowledge of inverse proportional and of percentages to be able to solve this. So, y is inversely proportional to the cube of x. So it's directly proportional to 1 over x cubed. And that means y equals k over x cubed. Calculate the percentage decrease in y when x is increased by 10%. So I'm going to start off with the original value of y, and I'm going to call that one yo, O for original. Yo is going to equal k divided by the original x cubed. Now I want to find the new y. Well, the new x is the old x increased by 10%, and that gives a multiplier of 1.1. So notice this. So when x is increased by 10%, if I've got 100% and I increase it by 10%, that's 110%. That's the multiplier of 1.1. So I can now substitute this in. My new y is going to equal k divided by my new x, but I'm going to put in this here, 1.1, the old times the old x, and then I'm cubing it. That is going to give me k over 1.1 cubed x naught cubed. So I've expanded the bracket with powers. What do I do now to get the percentage decrease? A little trick. I'm going to write it as 1 over 1.1 cubed times k over x naught cubed. Okay, and then I can work out what 1 divided by 1.1 cubed is. and it is 0.7513, but then this k divided by x naught cubed is actually my original y. So I've got a relationship between my new y and my old y. And what is this thing here? This is my multiplier. So if this is my multiplier, how can I work back to find the percentage decrease? Well, first of all, I can times it by 100, and this is going to be 75.13%. So what is the percentage decrease? I just have to do 100 minus that, and I've got a 24.9% decrease. And that is my answer. Now, I strongly suggest you lay your working out as carefully as this. I think it's a very tough question to just look at and figure out. In effect, we have just done 1 divided by 1.1 cubed and then changed that to a percentage and then worked out the percentage decrease. But I'm not convinced that gives full understanding of what's going on. You might think this is a bit over the top or even confusing, but it is the safest way, I think, of solving this problem. Okay, one more very similar to this, just to practice it a little bit more. So now y is inversely proportional to x squared, so I can write this, and then I can write y equals k over x squared. Again, no values, so I can't work out what k is, that's all right. So now I've got that the original y is equal to k divided by the original x. And what am I doing now? I'm decreasing x by 50%. So my new x is going to be 0.5 times my old x. So 50% decrease is the same as timesing by 0.5, because it's like I've got 100%, I'm decreasing by 50%, so I've now got 50%, and that's equivalent to 0.5. So my new value of y is going to equal k divided by my new value of x squared, but that is this thing here, so I'm going to put it straight in, 0.5 xo squared. And that's going to equal k divided by 0.5 squared xo squared. I'm going to again use the same trick. I'm going to write this as 1 over 0.5 squared k over x naught squared. This turns out to be 4 times, now remember this again is my old value of y. So what have I done? I've got that my new value of y is 4 times my old value of y. This 4 is 400%. But be very careful, that does not mean I've got a percentage increase of 400%. I actually have this 300% percentage increase. Because I start off with 100% and then I increase it by 300% to get to 400%. So just be careful about that. Whew, quite a lot of working. I've done it in the same kind of way, but be careful. That's my advice with direct proportion. You must remember the things I'm writing here. Okay, how to deal with it. It's very similar to direct proportion, except it's 1 over, but then the calculations end up being slightly different. Okay, I'm going to get you to practice some questions, practice, and get this sorted. Know when it's what to do when it's direct proportion and what to do when it's in inverse proportion.